Alright, this video is going to be on finding limits graphically. And since this is the first time we've really looked at limits in this class, we definitely want to know the definition before we get started. So the definition of a limit is the value a function f of x approaches. So the value a function f of x approaches as x approaches a particular value. So the question we're typically going to ask ourselves with this to make this idea make more sense is we're going to ask ourselves, at that x value, what is the y value, or what do I think the y value should have been? So I'm going to write that off to the side so I don't forget that that's a simple way of thinking of it. So at that x value, what is the y value? And the reason I can think of it as a y value is because in equations we always say f of x equals the function, and when we plug in the x value, that f of x becomes the y coordinate of our point. So f of x is really just a different notation and a different way of saying y. So with the notation, we want to be able to shorthand these answers so that we don't have to write out this sentence every single time. And so the shorthanded notation is the limit as x approaches a of the function is L. And the way that you read that out loud is you say the limit as x approaches a of the function f of x is L. Alright, so we're going to look at a few examples. And in all of these examples, the limit as x approaches 1 of f of x is 3. In all three of these examples. So here are the three examples. The first one is kind of the most typical case that you would see. This is if we take the function and we plug 1 into it for x, we're going to get 3 as an answer. So that point right there we're calling the point 1, 3. And that's pretty standard if you're asking the question, at that x value, what is the y value? At the x value of 1, the y value is 3. We've evaluated the function, that's what it says it is, and so it would make sense that the limit as x goes to 1 is 3. The next example is going to be very similar, but not quite so straightforward. So here we have almost the exact, well, the way I drew it looks exactly the same. Let me fix that. We have almost the exact same picture here, but at the point 1, 3 we have a hole. So if we go back and ask ourselves the question, at that x value, what is the y value? It looks like it should be 3, but if we were to plug 1 into the function, we would say that at 1, this function is actually undefined. There's an empty hole there. So here, even though this function is undefined when you plug in 1, it seems like the y value should have been 3. So we're going to say the limit as x approaches 1 is 3 because that's the y value that would make sense for that line. And then the third case here, and I think this case is the weirdest one, and the one that's going to, if one of the cases is going to mess with your brain, this is going to be the one that would do it. So again, we're going to say we have a hole right there at 1, 3, and right above that hole we have a point right here, and that point's at 1, 5. So here, when you plug 1 into the function, when you evaluate it and you actually plug 1 in, you would get 5 as an answer. However, at that x value, the y value that we would expect it to have, or the y value we would anticipate it having, is 3. So we're still going to say, even though I can plug in 1 and get 5 as the answer, I'm still going to say the limit as you approach 1 is 3, because that's the y value that fits the graph more clearly. All right, so underneath this, we're going to say the limit approaches 1, 3. So it approaches the point 1, 3. Or if we want to go back to the more general situation, the limit approaches the point A for the x-coordinate, L for the y-coordinate, from both sides. So what I mean from both sides is if you were to cover up the right side of this picture from the left side and you just kind of look at it, you'd still expect that y value to be 3. If you cover up the left side and look at it from the right side, you're going to expect that y value to be 3. So both of those sides agree. Now, it is possible to look at a limit from each side. We have left-hand limits and right-hand limits. And it is possible for those two limits to not be the same on either side. So we want to be able to look at them and compare them and see what conclusions we can come to after we find them. So, left-hand limits. The notation for a left-hand limit is the limit as x approaches a, and you put a little minus after it. So that's not saying that the a value is negative, that's saying we're going to look at the limit from the left side. So the limit as x approaches a from the left, and then a right-sided limit would be the limit as x approaches a from the right side. So when you're looking for a left-handed limit, you're going to look at the curve from the left of C, or sorry, not of C, from the left of A toward A. So you look specifically at the left side. So that would be as though in these previous examples I covered up the right side and all I cared about was this side. What does the y value look like it's going to be at this point? And I'm only looking at the left side. Similar on the right side, it means that you're going to look at the curve from the right of A toward A. So here is our example. And when you draw this, it's important that you have your circle. Oops, I'm sorry, you couldn't see that. It's important that you have your circle right there, but the slant of this line going up doesn't really matter. So make sure you have your circle at 2. And then we're going to go ahead and put another circle here and have a squiggly line going down. Again, the squiggle doesn't really matter. And then we have another point down here. Alright, so our instructions for the problem that we're doing with this example is we are going to find the limit as x goes to 0 from the left side of f of x, and the limit as x goes to 0 from the right side of f of x. So to do the left-hand limit, we start on the curve that's from the left, and we start on the left side of it, and then we work our way closer and closer and closer to it right there. So as you can see, if we look at this part of the graph, the y value that we would expect to see right there is a y value of 0. That's what I would expect to fill in that dot. So I'm going to say the limit as x approaches 0 from the left of the function is 0. We can also do right-hand limits. So I'm going to start at the curve from the right of the value, and then I'm going to work my way towards the value. And as I work my way towards it, it appears that the y-coordinate right there should be a y-coordinate of 2. So the limit as x approaches 0 from the right of f of x is 2. And finding the limits is different than evaluating, because if I was to evaluate the function at 0, if I wanted to plug 0 into the function, I would get this point right down here. If I evaluate this function, I find that f of 0 is actually equal to -3. So finding the limit is not necessarily going to give you the same answer as evaluating. All right, now we're going to have a little bit of a moment from Mean Girls. We're going to look at limits that do not exist. So limits, except we don't really say do not exist. We're going to say a limit that does not exist. So we're usually only talking about one. And to shorthand that, we're going to say D and E. The limit does not exist. All right, so the first one, the first situation where this happens, if f of x approaches a different number on the left side, so it'll be a from the left, and the right side. So this is kind of what we were talking about with the notes before. Here we have the limit as x goes to 0 from the left. We have the limit as x goes to 0 from the right. It appears that the y-coordinate is 0, but it also appears that the y-coordinate should be 2. And so we don't have any conclusive decision to make there. We're just going to say the limit as x approaches 0 in general does not exist, because these are two different numbers. So we can go ahead and draw that as a picture right here so we don't forget. So if I have this and this, then I would say the limit as x approaches 0 of f of x does not exist. And the rationale that I would give for that is because there are, instead of me writing out this sentence every time, I would just say there's two different values there. From the left side I have one value, from the right side I have another value. So underneath I'm just going to put two values as an explanation. So, and it might be helpful just as to kind of remember what these are. I'll go ahead and write two values off to the side so I remember that's what it's called. Alright, another case is when f of x increases or decreases without bound. So we're going to draw an example here as well. And let's say we have a graph that has a vertical asymptote. I'm going to go ahead and label that as the line x equals 2. So we have a vertical asymptote at 2. And let's say the graph goes like this. Now, I would say from the left side and the right side, these two numbers seem to be agreeing with each other. If I'm coming at 2, if I wanted to know the limit as x approaches 2, from the left side, I would say that's going down forever. That y-coordinate would be -infinity because it's going down forever. And then on the right side, as x is approaching 2, it's going down forever, so that y-coordinate would be -infinity. And I hope that you guys were maybe cringing as you heard me say the y-coordinate, because that's really what we're getting at. If I tried to write the point 2 with a y-coordinate of infinity, most of you guys would say that is not possible. You can't have a point where infinity is one of the coordinates. And that's exactly the reason why this is undefined. This limit does not exist because infinity as a coordinate to a point makes no sense at all. So we're going to say this does not exist, and that's because -infinity is not a valid y-coordinate, and we're going to go ahead and write unbound underneath. Unbound. Alright, and then the third reason that a limit could not exist is if f of x oscillates between two fixed values. as x approaches a. So, for example, if you were to look at the limit as x approaches 0 of the function sine of 1 over x, I'm going to show it to you real quick. So I went ahead and typed in sine of 1 over x. For the window of my calculator, I made the x values from negative pi to pi, because typically when we plug in an x value for sine, we're using like pi halves or pi fourths or something like that. And then the y values, if you remember sine graphs, they oscillate between -1 and +1. They go back and forth. So I set the range to my window to be between -1 and +1 so I can see what's going on. So if I'm looking at this graph and I want to know the limit as x is approaching 0, this is what that graph looks like. You can see it oscillate. I'm going to go ahead and change the window. I'm going to make it the same, but I want it to graph it for you so you can see it. There we go. So, and then it oscillates. So in this case, you can't tell the specific value that's happening as x gets to 0. It's going back and forth at that point. So let's go ahead and draw a little sketch of that. The graph comes from here, and then squiggle, and then it goes up. Your drawing doesn't need to be super accurate so long as you understand what was happening there. So we're going to say this limit does not exist, and the reason for that is that it oscillates.